everyone. Today is going to be your second video clip of the first week of this semester. The topics are about simple cubic lattice, body center cubic lattice, and face center cubic lattice, including their coordination numbers and packing factors. So let's take a look at these all figures. So this is models for simple cubic, body center cubic lattice, and face center cubic lattice. Look at this. The simple cubic, or the abbreviation SC. So simple cubic lattice consists of one lattice point on each corner of the cube. Each atom at a lattice point is then shared equally between 8 adjacent cubes. And the unit cell therefore contains in total 1 atom. So if you shop it, right, inside of the cube, right, at the corner here, it contains only 1/8 of atom. So we have 8 corners. Total will be 1 atom in the simple cubic lattice. How about the body center cubic, BCC lattice? So this is it. It has 1 lattice point in the corner of the unit cell in addition to 8 corners points. So this is like a simple cubic, right? Plus 1 in the middle. So the total would be 2 atoms. So 1/8, right, multiplies by 8. So this is just like simple cubic plus 1 in the middle here. So this is this one. A net total of 2 lattice points per unit cell. Let's move to the FCC lattice, or the face center cubic lattice. It has lattice points on the faces of the cube. So one cube, how many faces do we have? Look around, right? We have 4, and up and down, right? Top or bottom. So 4 plus 1 and 6. So total will be 6 faces. So let's take a look. This is just like simple cubic, right? 1/8 multiplies by 8. So we have 1. So this is 8 corners from the, or 8 corners plus 1/2 inside of the cube, right? If you shop it inside of the cube, for each face contain only 1/2 of the atom multiplies by 6 faces. So total will be 3 from the faces. So finally, a total of 4 lattice points per unit cell. Let's learn more about some more definitions. In a Brava lattice, the neighbor atoms that have the closest distance from a point of interest are called first nearest neighbors. And if neighbor atoms have the second closest distance, they're called second nearest neighbors. Each point of a Brava lattice has the same number of nearest neighbors. So this is a property of the lattice. The number of the nearest neighbors called coordination number of the lattice. We will take a look at examples one by one. So this one I already give you the definition. And again, coordination number is the number of nearest neighbors. Okay, so we're gonna have to try to count because this is the word number, right? Number, I have to count. So this is the figure that I already mentioned. So at the middle, right, you just count 1 atom directly. So at the corner, right? At the corner, 1/8, and at the edge is 1/4, and at the face is 1/2. Okay, let's count the numbers of nearest atoms for simple cubic lattice or SC. So I have 1, 2, 3, 4, 5, 6, 7, 8. 8 unit cells here, right? So if I sit right here, okay, sit right here. Look, I sit right here. So we're gonna count 1, 2, 3, 4, 5, 6, all these figure, right? So total will be 6. So the coordination number for simple cubic lattice is 6. How about if they ask you more? How about the closest distance? So we have to calculate, right, to the neighbor atom. So from here to here, how far is it? It's just a length of a cube, which is A, okay? So this picture here is a model that show you that like inside of the cell, right, at the corner contains 1/8. Okay, let's move to BCC, body center cubic lattice. Okay, 1 in the middle here, right? So look up. So we have got 8. Then look down, have another 8, just like this, okay? So here, how many coordination number for BCC lattice? 8, right? How about the closest distance to the neighbor atom? So we sit here. Okay, so this is the picture. So we sit here. You have to review the Pythagoras theorem. So this one, the length is A. So this is A. So this is A. Right here is square root of A, right? So this is A, square root of 2A. So this, sorry, so this is square root of 2A. So right here, from the diagonal length here, it's gonna be square root of 3A, but half of it, right? Half of it is gonna be divided by 2. So square root of 3 divided by 2. This picture is the demonstration of number of atoms per unit cell for BCC, right? So we already have done it. So it's 1, right, in the middle, plus 1/8 times 8 corners. So total will be 2. Move to face center cubic lattice. Coordination number is 12. Let's see if we can make it 12. This one is a little bit tricky. Why is it a little bit tricky? Because right now, nothing in the middle, right? So there are 6 faces, and each face contains like 1 here, okay? Or inside contains only 1/2 of the volume. So you have to sit right here, okay, on the side, right? Are you with me on the side here? Okay, so we go up this way, okay, along the green line and down, right? And here and here. So we count as 4 already. And then we go, so this is the left box. So we go to this atom, right, on the back, on the back. And this is in the front of the left box. So this one. So we have 1, 2, 3, 4, 5, 6. Again, go here, right? So we look at the right box. So at the back of the right box, the front of the right box. So 4 plus 4 is 8 already. Now from here to the top of the left box, right? And to the right box, this is on the top too. So count 2. Same down at the bottom of the left box, bottom, right, of the right box. So count another 2. So 4 plus 4 plus 4. 4 multiplied by 3 is 12. Okay. If you didn't follow, maybe listen again, okay, by yourself. And number of atoms per unit cell is 1. So 1 plus what? So I think this is this one we have to redo again. So let's see. So at the corner, so 1/8, right, multiply by 8. So we have 1. And how about all the faces? We have 6 faces, right? And each face in the cube contains 1/2. So this is number 3. So this one, 6 faces. So total will be 4. So this is wrong, okay? Sorry about that. Now let's compute, right, that the distance from the center atom to another atom sitting on each 4 corner on the same plane is A divided by square root of 2. Okay, so this one, I will leave you as the homework, okay? So what you have to prove, you have to prove that the distance to the nearest neighbor atom is the same. Okay, so probably okay, if I draw a figure for you, so this is right triangle, right? Right triangle. We know this is what? A. And this distance is what? Is A, right? So this would be what? Remember? A square plus A square. I make it X, right? For now. So this side, right? It's gonna be this one is 2A square, and then I take the square root of this. It's gonna be square root of 2A. But since we want only half, so this is half, right? So it's gonna be square root of 2A divided by 2, which is A divided by square root of 2. So we proved this already, right? So the rest, can you try to prove by yourself and show that they are the same? Okay, let's move to packing factor for 3D crystal structure. Since we already know SC, BCC, and FCC, we're gonna calculate the packing factor for these 3 structures first, and then the rest will come back again when we learn more about some common crystal structures, okay? Let's take a look. What is the meaning of the packing factor? Remember the first lecture, I show you some nature things like they want to pack something, right? I mean, sometimes they don't like randomly, packing randomly. They I mean, like could be human also. Sometimes we want to pack like efficient, right? Like efficiency. So we want to pack as much as possible. So here is the thing. So we will assume that the one atom is like a, I'm gonna draw a picture. So we will assume that one atom, right, is sort of like solid, okay? But in real, it's not solid. You know that like electron is just like cloud, right? Like a cloud. But we have to use approximation like a solid, okay, for example. And then we want to pack all these ball or the atom inside of a cube. And it could be simple cubic, could be could be body center cubic, or it could be face center cubic, to see how much, right, we can pack the most. Okay, so packing factor from the definition is the sum of number of atoms, right? So we already count for each crystal structure, multiply by the volume of atom, right? So to see how much total of the volume of atoms, right? Imagine that, divided by the volume of the unit cell, okay? So at the denominator, it's gonna be the same, right? I mean, the volume of the unit cell. So if it's all the cube, it's gonna be just A cube, right? So the difference will be only these terms, okay? Yeah. And we already know this, right? For each crystal structures. And then atom volume, this is like a sphere, right? We imagine it's like a sphere. The volume of a sphere is going to be 4 divided by 3 pi r cube, okay? And notice that the packing factor is dimensionless and always less than unity, okay? Okay, let's do the simplest one. Simple cubic. First, you have to find out what is the relationship between the length of the cube and the radius of the atom. Okay. So from this picture, this is the length of the cube is A. Okay, I'm gonna use a red pen then. So we know that this is R, and this is another R, where R is the radius of the R sphere or the atom that we assume is like a solid sphere. So A is 2R. Packing factor, from the definition, right? Right now we calculate for simple cubic. Remember, we count already how many atoms in the cube? 1. But the volume is 4 divided by 3 pi r cube divided by the volume of the cube. So it's A cube. And then you replace, we know A is 2R. So R is what? A divided by 2. So notice that the A cube will cancel out, right? So this cancel out. The answer is pi over 6, 0.5236. Let's do for BCC. Again here, the length of the cube is all A, right? All A. And notice this. This is A. Sorry, this is R, right? And this is R. But for BCC, if you point a straight line from one corner to another corner in diagonal, right? In diagonal, so this distance is gonna be 4R, right? And look at the base, okay, at the base. So this is A, and this is A. Here is gonna be square root of 2A. Actually, I proved this already. If this is A and this is A, this length is gonna be square root of A. So what we have to focus is this triangle. Okay, let's make a drawing. So we focus on this. This and down like that, okay, in diagonal. And this is A. The square root of 2A. And the dot, dot, dot here, right? From here to here is 4R, right? So total, so with the right angle here, so from this, we're gonna get 4R total square equals square root of 2A square plus A square. So this is only 3A square is 4R square. So 4R is square root of 3A. So R is square root of 3 divided by 4A. So we'll use this relationship to plug it in the packing factor. So packing factor for BCC is, okay, remember the definition, we have to count how many atoms in the BCC. At the corner, I'll go that quick, 1/8 multiplies by 8 plus 1 in the middle. So 1 plus 1 is 2. So we have 2 multiplied by, we assume the atom is solid sphere, 4 divided by 3 pi r cube, right? Divided by the volume of the cube is a cube. Now you replace r with this right here. So the answer, you can solve this out. The detail by yourself, the answer is square root of 3 pi over 8. So this is 0.6802. Next, packing factor for FCC. Okay, for FCC, we're gonna draw a right angle triangle at the face. So this is the length A. This is the length A. And you see that this is 4R. So we have 4R and this is A and this is A. So now the relationship is going to be 4R total square equals A square plus A square. So this is 2A square. So 4R is square root of 2A. So R got the relationship between R and A, square root of 2 divided by 4A. Then we do the same. Packing factor for FCC. Count how many atoms in the FCC cube, right? Remember, 1/8 multiplied by 8 corners plus 1/2, right, on the face, multiplied by 6 faces. So total would be 4. It's going to be 4 multiplied by 4 divided by 3 pi r cubed. So this is the volume of one sphere, but we have 4 solid spheres. Divided by, again, the volume of the cube, which is which is A cube. And then you plug in R is square root of 2 divided by 4. We have pi square root of 2 divided by 4. And here is A cube divided by A cube. Solve that out for details. We have square root at the end. We have square root of 2 pi divided by 6. So it's 0.7405. That's the answer. Okay, great. So this lecture I will finish for now. And next lecture, I will talk more about primitive unicell, weaknesses cell, and common, it's like a conventional unicell, the common one. And also we will come back to packing factor for some common structures, okay? And I will show you more common structures like diamond. You know what diamond is, right? And hexagonal, okay? And maybe some other example like you know this one for sure. I'm not sure if you know sodium chloride, right? Something like that. The easiest one, okay? So I think that's it for today. Okay, thanks for listening. See you, bye.